Hello, welcome to the second part of the video tutorial on solid modeling in NCLab with PLaSM. In the second part I will show you how to create additional simple objects such as prisms, cones and general convex polyhedra, and I will also show you how to transform objects using scaling, translations and rotations. For this, let me first close this nice model and open a fresh Python project. As the first thing, I will import the PLaSM library. It's actually PyPLaSM because of the Python wrappers. And the first command I will show you now is called convex hull. This is a very powerful command because it will construct the convex hull of an arbitrary set of points that you specify. So let's illustrate this on a simple tetrahedron. This is the smallest 3D object with just 4 points. So we'll just create a Python list that contains 4 points. First one is minus 1, 0, 0. Second one can be 1, 0, 0. Third one can be 0, 2, 1. And the last, for example, 0, 1, 2. Now the application of the convex hull command is very simple. You just supply the list of points and that's it. And in the last step we visualize again. So lab view, our tetrahedron and our color. Okay, for this I need to define a color, which I forgot. And I'll use a light gray again as before. And now we should be ready. So what you see in this new WebGL widget is the tetrahedron that you just created. I would like to use this opportunity, since we are talking about the convex hull command, to also show you the scripting part of PLaSM. This is a very powerful feature because you can create the 3D geometries by programming. In fact, let me illustrate this by creating a cone. So for this we will first import some functionality from NumPy. NumPy is a major numerical computations library in Python, and we'll use it just for sine, cosine and pi now, because we will need to create points on a circle. Let's define some parameters such as the height of the cone, radius can be, for example, 5, and the number of subdivisions for the curved surface. This is the same as for cylinder that we saw in part 1. Now I will create an empty list of points and do a simple loop to add to this list the points that are lying on the circle. So this will be something like the radius times cosine of the angle, radius times sine of the angle, okay, and 0 because they are on the unit, they are on the xy plane. Now the angle will be something like I times 2 times pi, but divided by n. And in fact this loop, unless I made a typo, is enough to put points on the base circle of the cone. And in the last step, I will append a tip, which will be at 0, 0h. And the convex hull will take care of the rest. So what I just type is cone is defined as convex hull of those points. And we just need to show it. So lab.view, our cone, and our color. And unless I made some typos, this will be okay. Of course I made. So yes, my N is capital. And here is our cone. Okay. Now again, you can still see some imperfections in the curvilinear surface. If you wanted, you could increase this parameter to 128 from 64, and that would take care of it. But now my goal is different. I would like to show you scaling, how we do scaling in PLaSM, and maybe I can use the cone for this. So after we create this cone, we will use the command scale, and the last parameter of this command is the object that we scale. The first parameter is a list of directions in which we want to scale. So if I wanted to scale in all three, I would write something like 1, 2, 3. But right now, I want to scale only in the y direction, so I just write it 2. And in the second argument, we put a corresponding list of constants. Say that I want to shrink the cone to 50% in the y direction. This is done like that. Okay. And we can see here that our cone indeed is much more narrow in the y direction. If you look from it like this, we can see this clearly. This is an ellipsoid. It's an ellipse on the base. Let's do one more example. In addition to scaling in the y direction, I can scale also in the z direction. And let's reduce the height of the cone to 20%. Now this cone is pretty flat. I would like to emphasize that you can do this with any object that you create in PLaSM. I'm just illustrating it on a very simple one now, and it will just work. So we can move to the next command, which is translation, and for this I would like to create a new object. So let me create, for example, a brick B. It will be a cuboid with base 1 by 1 and height 3. So it will be actually a square pole, something like this. And let's view it. Of course, color. Okay, this is now our pole, and let's translate it. We will define a new break B2 that will be obtained by translating B. Again, the object is the last argument. The arguments are very similar to the scaling. In the first argument, we put a list of directions for the translation. In fact, this is the translation vector. Except if you just want, say, translate in the y direction, you put just a number 2. Okay, just the relevant coordinates. And let's say that we want to translate by 2. Now, if we want to see what happens, we would like to show the original brick along with the new one, and for this we can use the command struct, which will create a compound of any number of objects. So now the view will show not only the new one but also the original brick, and we'll be able to see how the translation worked. And indeed, we can see this one in the front is the original brick, and the one in the rear is the one that we moved by 2 in the y direction. And as a compound, you can work with it, rotate it, and so on. And again, you can translate any object that is created in PLaSM. Let me now move to the last command, which is rotations, and for this I will create a cylinder. So the cylinder will be will have, say, radius 0.5 and height 3, and we'll use 64 divisions of the curved surface, and let's view it first. This should do it. Okay, so now the center of the originate system is here. If I want to rotate my cylinder with respect to his own center of gravity, first of all I need to translate it by 1.5 down in the z direction. So let's do it. I will translate my cylinder in the third direction by minus 1.5. Of course, now we will not see anything because the axes are not shown. But when I rotate it now, let me rotate it. Let me create a cylinder 2 obtained by rotation of my cylinder. And how the rotation works is that in the first argument you give the 2 axes in which plane the rotation will occur. So it would not make sense for me to write 1 and 2 because I would just rotate the cylinder in the XY plane and the result would be the same cylinder. Instead I can do 1, 3, and the second argument will be the angle, so this can be pi half. And I will show the new one in addition to along with the old one using again the struct command. So like this. And unless I made typos, this would show us a nice cross. Of course I did. Struct. Okay, this is what I wanted to see. This is a nice cross. Of course we could add one more cylinder 3 by rotating in the second and third axis by pi half and adding the cylinder 3 into the struct. This would add one more cylinder like this in the remaining direction, but I will leave this to you for your experimentation, and instead I would like to finish now and we'll continue with part 3 in a moment.